I want you to take a second and just look around at the physical world right now.
Right.
Like whatever room you're sitting in or the device you're listening to this deep dive on, or even just, your own hands resting in front of you, everything you see, everything you can actually touch, it has mass,
Right.
right? It has weight.
Oh, absolutely.
Yeah.
Everything tangible.
Yeah. And usually when we think about weight in our day-to-day lives, we think about it as something, well, totally predictable and logical. You put an apple on a scale, weighs what an apple weighs, you add a second apple, and boom, the weight doubles.
It makes perfect intuitive sense.
Exactly. It makes intuitive sense. But then when you zoom all the way down to the absolute fundamental building blocks of reality, like those tiny subatomic particles that actually make up that apple, and the scale and that predictable logic it completely falls apart.
It really does. It shatters.
And it leaves us staring at this massive unanswered question at the heart of physics, which is, why do these tiny particles weigh exactly what they do?
Yeah, and this is a question that has genuinely kept the greatest physicists awake at night for decades. I mean, when you step down into the quantum realm, the diagnostic landscape is, honestly, it's incredibly murky.
Right.
We have this expectation of, like, elegant precision in physics, right? But the masses of these fundamental particles, they seem almost completely random. It's easily one of the most glaring holes in our understanding of the universe.
Which brings us to exactly what we're digging into today, our mission for this deep dive. We're looking at a really fascinating new theoretical physics paper that asks a pretty bold question. What if those seemingly random weights aren't just chaotic noise?
Right.
What if they actually sit on a hidden, elegant mathematical ladder that we simply haven't noticed yet?
It's such a brilliant premise, but to really appreciate how radical this idea is, we kind of need to set the stage by looking at the core problem in particle physics right now.
Let's do it.
So think about human measurement systems: an inch, a mile, a kilogram.
Right. Totally made up.
Exactly. Those are entirely arbitrary. We made them up based on human conventions, just to make trade and building easier. But particle masses are different. They're empirically observed physical realities. They just are.
They exist independently of us.
Yes. And in the standard model of physics, which is, our absolute best, most rigorously tested rule book for how the universe works, these masses span wildly different orders of magnitude without any obvious reason.
Okay, let's unpack this for a second, because when you say wildly different, we aren't just talking about, like, a bowling ball versus a golf ball, right? We're talking about mind-boggling differences in scale.
Oh, yeah, completely mind-boggling. To give you a sense of it, you have the electron, which is incredibly light.
Right.
And then you have the top quark, which is massively heavy. And the difference between them isn't just, a factor of 10 or 100. The top quark is over 300,000 times heavier than the electron.
Wait, over 300,000 times?
Yeah, like if the electron weighed as much as a standard house cat, the top quark would weigh as much as a fully loaded commercial airplane.
Wow. Okay, that's a gap.
Exactly. And this huge erratic spacing between the masses is what physicists call the hierarchical spacing problem.
Right. But, okay, let me jump in here. Doesn't the standard model explain where mass comes from in the first place? Like, what about the Higgs mechanism? I thought that was the whole point of discovering the Higgs boson, years ago.
That is a fantastic point, and it's a really crucial distinction we have to make here. So, yes, the standard model explains how particles acquire mass, mostly through interacting with the Higgs field.
The famous field.
Right. You can think of the Higgs field as a sort of invisible cosmic syrup that just permeates all of space.
Cosmic syrup, I like that.
Yeah, it's a great visual. So as particles move through this syrup, some interact with it very weakly. They just zip right through and remain very light, like the electron. But other particles, they drag through it heavily. They interact strongly with the syrup, and thus they have a large mass, like our airplane-sized top quark.
Makes sense.
But here's the catch. The standard model does not dictate why a specific particle interacts with the field at the exact strength that it does.
Oh.
The values of those interactions, what we call coupling constants, they have to be measured experimentally and literally plugged into the math by hand. The model cannot predict them. It's an unresolved structural mystery.
So we know the mechanism of how they get heavy, the syrup, but we have no earthly idea why they are assigned these specific, vastly different weights.
Precisely. We know the how, but the why is entirely missing.
So enter the paper we are analyzing today. Now, just to be super clear to you listening, the researchers aren't claiming to rewrite quantum physics here or like throw out the standard model.
No, not at all.
They're offering what they call an exploratory approximation model.
Yes. And before we get into the specific mathematical pattern they propose, we really need to understand the methodology of how physicists even search for order in that kind of chaos.
Because they aren't working from the top down.
Right. The researchers use an approach called a phenomenological ansatz.
Okay, phenomenological ansatz. That sounds incredibly intimidating. What does that actually mean in plain English?
Yeah, it's a really dense term, but it's actually a very simple concept. In physics, an ansatz is essentially an educated mathematical guess. It's a trial structure.
An educated guess, okay.
Right. The researchers are not deriving this pattern from first principles. They aren't saying, based on the fundamental mechanical laws of quantum field theory, this equation must be true.
Because they don't know the why yet.
Exactly. Instead, they are taking the known measured masses of the particles and testing a descriptive mathematical framework against them just to see if a recursive structure gives us a useful perspective on the data. They're working backward from the empirical observations to see if a hidden rule fits.
So it's kind of like, okay, let's say you have a locked safe, but you don't have the factory blueprint for the internal mechanical gears.
Oh, that's a good way to look at it.
Right. Like you don't know exactly how the tumblers are shaped inside the door.
Right.
But instead of trying to violently dismantle the safe, you just start applying different numerical sequences to the dial on the front.
Yes.
You aren't claiming to understand the tiny springs inside. You just want to see if a specific sequence of numbers suddenly makes the lock click open.
That is exactly what an ansatz is. They're turning the dials to see if a structural pattern emerges from the noise. And what's fascinating here is the specific sequence they are testing on this cosmic combination lock.
Because it turns out their whole guess is built entirely around the number 3.
The magic of base 3.
The magic of base 3. So how does that work?
Well, they're using a ternary or base 3 scaling structure. The core formula they propose in the paper is, well, it's shockingly simple for quantum physics.
Like how simple?
They propose that particle masses can be approximated by taking the number 3 and raising it to the power of an integer divided by 2. So mathematically, it's just 3 to the power of n over 2.
Okay, let's break that down. So in that formula, 3 to the power of n over 2, the n is just a basic integer, right? Like a positive or negative whole number. -7, 0, 2, 5.
Yes, exactly. The n is an integer-valued index. Think of it as the specific rung on the ladder.
Okay, we're wrong on the ladder.
But here's the clever part of the math. By using half integer powers, which is the n divided by 2 part of the equation, the formula creates intermediate steps. It creates a denser recursive ladder across what physicists call logarithmic mass space.
Logarithmic mass space. Okay, let's translate that because when I hear logarithmic, I think about compressing massive scales into something readable. Is this like the keys on a piano?
Oh, that is an excellent analogy. Let's explore that.
Because if you look at a piano keyboard, the physical keys are spaced out evenly, right? Just right next to each other.
Right.
But the actual sound frequencies they produce are growing exponentially. Like the frequency doubles every time you go up an octave.
Yes, exactly.
So if you map the actual sound wave frequencies on a normal linear ruler, the high notes would be miles away from the low notes. But our ears process it logarithmically, so we just hear a repeating, evenly spaced structure of octaves.
That's a perfect way to describe it. A linear scale focuses on absolute differences, which for particles looks like a chaotic, unreadable mess of zeros.
Right, because the top quark is miles away from the electron.
Exactly. But logarithmic mass space compresses that data. Successive changes in our integer n correspond to multiplicative scaling steps, rather than just adding a little bit of weight each time.
So it scales up and multiplying.
Yes. When you move up or down a rung on this mathematical ladder by changing the value of n, you're scaling the mass exponentially. And by allowing n to be both positive and negative numbers, this single unified exponential structure can span the incredibly light particles down in the negatives all the way to the massively heavy ones up in the positives.
Oh, wait, I have to push back here for a second.
Sure, go ahead.
Because if yin can be any integer, right? Negative or positive, but you're basically going on forever.
Mm-hmm.
Aren't you just giving yourself an infinite number of slots to drop a particle into?
The data fitting concern.
Yeah, like if you have enough random numbers on a dial, eventually you can make an equation fit almost anything, right?
Yeah.
Isn't there a huge risk here that this is just a cosmic party trick where we're, I don't know, painting a bullseye around wherever the arrow happened to land?
That is the exact right question to ask, and honestly, it is the primary danger with any ANSYS. You have to be deeply skeptical of data fitting.
Right.
But the answer to your question is no, and here is why. This formula is incredibly constrained.
How so?
Well, this isn't a complex equation with a dozen adjustable parameters or some fudge factor that you can tweak until the data perfectly matches. It is extreme mathematical simplicity.
It's literally just base 3 and a single integer.
Exactly. If this were just random data fitting, the actual particle masses wouldn't cleanly hit these rungs. They would fall awkwardly between the integers at, say, n equals 3.14 or n equals negative 7.8.
Oh, I see.
Yeah, the absence of parameter-rich, complex fitting procedures is actually what makes this paper so compelling.
Okay, so to see if this base 3 math actually survives that skepticism, we really have to look at how it maps against the real universe. We have to test it against the empirical masses that scientists have actually measured in particle colliders.
We do, and the researchers put all of this into Table 1 of their paper.
Yeah, and the empirical results they compiled in Table 1 are, well, they're the anchor of this entire theory, really.
They are. When they apply the simple integer index, that n value, the normalized approximations, match the actual observed masses with an accuracy that exceeds 98% for the vast majority of particles.
Which is just a wild number to see when you're talking about something as famously chaotic as quantum mass.
It's unprecedented, really.
So let's look at the actual data because it really brings us out of the theoretical realm.
Yeah.
First, though, we have to talk about the two main tribes of particles in the universe. Fermions and bosons.
Right.
Just to keep us grounded, what is the quick difference between those two?
Simply put, fermions are the building blocks and bosons are the glue.
Building blocks and glue. Okay.
Yeah. Fermions are matter particles, things like electrons and quarks that make up physical stuff. Bosons are force carriers, particles like photons or the Higgs boson that transmit forces and interactions between the matter particles.
Perfect. So let's take a famous fermion, the electron. When you map its mass into this base 3 formula, the electron sits incredibly comfortably at an index of n equals 3.
It does.
And when you run the math, the match to its actual real-world mass is 98.3%.
And remember, that's a very light matter particle. But then you swing to the other extreme, the extraordinarily heavy top quark.
Right, the big one. The heavy top quark sits right near the center of this ladder at n equals 1, and the formula matches its actual mass with 99.7% accuracy.
It's astonishing.
And it works for the glue, too. The bosons, even the famous Higgs boson itself, the particle responsible for the cosmic syrup we talked about, it fits beautifully on this ladder at n equals negative 8 with a 98.6% match.
It spans the whole spectrum.
But wait, let me put my skeptic hat back on for just a second here.
Put it on.
We hear 98% and we think, wow, an A on the test. That's amazing. But we're talking about precision quantum physics here. A 2% error margin in a multi-billion-dollar particle collider is massive.
It is.
So is that 2% failure rate a sign that the math is fundamentally flawed, or are the error bars in quantum measurements somehow accounting for that?
No, it's a highly necessary critique, and the researchers address this directly in the paper. The framework is explicitly presented as an exploratory approximation, not an exact predictive field theory.
So it's not trying to be perfect to the final decimal.
Exactly. We aren't expecting it to be accurate to 12 decimal places because we are mapping an emergent, coarse-grained structure.
Coarse-grained, meaning like the big picture shape of it.
Right. Furthermore, for some of these particles, particularly the quarks, their masses actually change depending on the energy scale at which they're measured.
Wait, their mass changes?
Yes, it's a phenomenon known as running mass. So defining an absolute static mass for a quark is already incredibly tricky.
Oh, I had no idea.
Yeah, it's a moving target. Given the inherent uncertainties in quantum mass definitions, finding a single parameter-free exponential base that hits 98% accuracy across completely different particle families spanning multiple orders of magnitude, it's mathematically highly significant.
Because it's too neat to just be an accident.
Right. It strongly suggests the mass spectrum is exhibiting non-random organization.
And here's where it gets really interesting. This is the part of the paper that absolutely blew my mind when I read it.
I think I know what you're going to say.
When you look at the different categories of particles in Table 1, the researchers highlight a specific group they call stable and visible matter.
Yes, this is the critical subset. This is the stuff that actually makes up our everyday, tangible reality.
Right. It includes the up quark, which the formula places at an index of n equals -7, the down quark, which sits at n equals 7,
Hmm.
and the electron sitting at n equals 3,
Yeah.
up quarks, down quarks, and electrons. Those three particles combine to make protons and neutrons, which make atoms, which make molecules, which make, well, everything.
Everything.
You, me, the chair you're sitting on, the stars in the sky, and they correspond exclusively to odd-valued indices, -7, 7, and 3.
It is a truly remarkable finding.
Let's stop and really appreciate that for a second. Think about what this implies. Out of the vast, chaotic soup of quantum possibilities, the only particles that are stable enough to actually build a lasting, visible universe, the particles that constitute human biology and conscious observers, they all sit exclusively on odd-numbered mathematical rungs of a base 3 ladder.
Exactly. And to understand why that is so profound, you really have to look at what is sitting on the even numbers, or at zero.
What's left over?
Well, that odd index structure does not appear uniformly across the other categories. Unstable particles that decay in fractions of a second, or invisible ghost particles like neutrinos that just pass right through normal matter, they occupy the other mathematical slots.
So the fact that we exist at all, the fact that there's a stable universe, is tied to this odd number mathematical syntax.
Yes. It indicates the presence of asymmetric grouping behavior within the broader hierarchy. It tells us that these integer states are not just arbitrary numeric placements. There is an underlying structural syntax here.
Syntax.
Right. The stable, visible universe occupies a very specific mathematical territory within the larger equation.
A structural syntax. So this odd number rule for visible matter isn't just some isolated anomaly. Like when we zoom out and look at the whole ladder, are there other patterns?
Absolutely there are. When you map all the indices from the table together, deeper architectural groupings immediately begin to emerge. The integer assignments display recurring structural relationships. They cluster together in highly specific ways.
What kind of clusters? What does the syntax actually look like in the data?
Specifically, they form triplet configurations. The integers group into sets of 3, and a recurring 2+1 organizational pattern appears over and over again.
A 2+1 pattern. Okay, what does that actually look like? Give me an example.
Let's look at the neutrinos. Like we said, these are incredibly elusive, nearly massless particles. In the table, the electron neutrino sits at n equals 0, the muon neutrino is at n equals 1, and the tau neutrino is also mapped at n equals 1.
Okay, 0, 1, 1.
Exactly. So the triplet for the neutrino family is 0, 1, 1. You have two closely related integer values and a third offset value, a 2+1 pattern. We see similar asymmetric groupings across other categories too, where two indices share a relation, and the third sits just outside it.
And beyond the triplets, there's also this overarching symmetry to the whole ladder, right?
Yes, there's a beautiful symmetry spanning the entire mass hierarchy using mirrored positive and negative states.
Which is so aesthetically pleasing.
It really is. You have the strange quark at n equals 4 and the muon sitting perfectly opposite at n equals -4. You have the down quark at 7 and the up quark at -7. The W boson is at n equals 8 and the Higgs boson mirrors it exactly at n equals -8.
So the ladder isn't just building upward infinitely into heavier and heavier stuff. It's perfectly balanced on both sides of 0.
Right.
It's like an intricate mobile hanging over a crib, perfectly counterweighted, the positive mass values on one side balancing out the negative indices on the other.
That's a great image, exactly. The scaling structure seems to span logarithmic mass space through mirrored hierarchical levels rather than just, piling up indiscriminately in a positive direction.
If we connect this to the bigger picture, it reminds me of that moment in a mystery movie when the detective shines a black light on a seemingly blank wall and suddenly an intricate glowing geometric grid is revealed.
Oh, I love that analogy.
Because we looked at the standard model masses for decades and saw just a chaotic splatter of numbers, like a Jackson Pollock painting. But logarithmic base 3 scaling is the blacklight. We turn it on, and suddenly we see mirrored symmetries, 2+1 groupings, and visible matter strictly obeying odd number rules.
And what makes that blacklight revelation even more compelling is that this 2+1 asymmetric triplet behavior mirrors other deeply established, known ternary organizational patterns in physics.
Wait, really? Where else do we see base 3 or 2+1 patterns in the subatomic world.
Think about proton and neutron composition. These are the hearts of atoms, right?
Right.
A proton is constructed from 2 up quarks and 1 down quark. A neutron is 2 down quarks and 1 up quark.
Two of one of the other.
Exactly, 2 of one of the other. It is a fundamental 2+1 triplet-based structure built right into the core of the Standard Model itself.
Oh, wow. That's hiding in plain sight.
Yeah. Now, the paper is rigorously careful not to propose a direct, literal equivalence between the physical core configurations and these abstract mass index assignments.
They're not saying it's the exact same mechanism.
Right, they're playing it safe. But the recurrence of asymmetric triplet configurations strongly indicates that we are looking at a coarse-grained organizational regularity. Nature seems to deeply favor these repeating structural motifs.
So with this beautiful geometric grid revealed, this incredibly simple base 3 ladder that somehow catches 98% of the universe's weights, the ultimate question remains. Does this mathematical pattern reflect a physical, mechanical reality, or is it an illusion? Are we just finding shapes in the clouds?
It's the ultimate question,
Yep.
and the researchers are remarkably cautious in their conclusion, which honestly is exactly what gives this paper so much credibility.
They aren't overpromising.
Right. They reiterate that their framework remains strictly phenomenological. Remember our safe analogy from earlier?
Yep, the combination lock.
Right. They have found the combination sequence that opens the lock, but they have not dismantled the door. There is no established physical derivation from quantum field theory yet that proves why this base 3 scaling happens mechanically.
We still haven't found the gears. We don't know what the springs look like inside.
Precisely. The analysis does not explain the physical mechanism behind the ternary scaling. It could reflect deeper structural principles that we just haven't mathematically discovered yet, like in string theory or quantum gravity.
Sure.
It could be an emergent recursive behavior of complex quantum fields interacting with each other. Or, as we must always admit in theoretical physics, it could simply be a profound numerical coincidence.
Which raises a really important question for you, the listener.
Yeah.
Because you might be, walking the dog right now or driving to work.
Right.
And you might be wondering, why should you care about abstract particle physics and a base 3 mathematical ladder? I think it deeply matters because it completely challenges our basic human assumptions about randomness.
Oh, absolutely.
We are so quick to look at a dense data set at work or a complex situation in our lives and just say, that's just random noise. There's no pattern there.
That is a profound takeaway.
We assume that if we can't see the order immediately, the order just doesn't exist. But this paper highlights the immense value of looking at old data through an entirely new lens.
A new perspective changes everything.
Yeah. By stepping away from linear measurement and mapping these masses on a logarithmic scale, by applying a simple exponential base, these researchers found breathtaking symmetry where the greatest minds in physics only saw noise for half a century.
It's incredible.
It's a reminder that when things seem chaotic, we might not be looking at chaos. We might just be using the wrong scale to measure it.
And this raises a crucial point about how science actually progresses. While elegant math often points the way to profound new physics, think of how the periodic table of elements was organized mathematically by Mendeleev way before humanity even knew about the existence of protons and electrons.
Oh, right. He left blank spots for undiscovered elements.
Exactly. The math led the way. But we still must wait for future rigorous work before calling this a new law of nature. The researchers themselves lay out the next steps. We need to test alternative scaling bases. What if base 4 or base 5 works better?
You've got to try and break it.
Yes. We need to introduce stricter index constraints, and crucially, we need to examine whether similar recursive exponential structures appear in other empirical physical hierarchies outside of just mass. The scientific method requires us to try and break the model to see if its bones hold up.
So we've taken quite a journey today on this deep dive. We started with a fundamental problem, the chaotic, wildly varying weights of the universe's basic building blocks. A hierarchical mess that has honestly confused physicists since the dawn of the quantum age.
It really has.
And we explored a brilliant phenomenological framework that suggests they might actually sit comfortably on an elegant base 3 mathematical ladder, a ladder that accurately maps their mass with over 98% accuracy.
Which is no small feat.
Not at all. We saw how the very stable, visible matter making up our bodies relies entirely on odd-numbered mathematical rungs, and how the whole cosmic system balances out with beautiful symmetries and mirrored states.
It is a compelling reminder that our standard model, for all of its incredible, historically unprecedented predictive success, it might still have secret, beautiful architectures hidden beneath its floorboards, coarse-grained, recursive ordering features that we are really only just beginning to conceptually illuminate.
And that leaves us with a final, lingering question for you to ponder long after this audio stops playing. Look around at the physical world again. Think about the gravity holding you to the floor or the screen you are looking at right now. If the very weights of the fundamental particles that make up the strict reality we live in are secretly dictated by a recursive, fractal-like mathematical ladder, what other random or arbitrary facts of our daily lives might secretly be dancing to an undiscovered mathematical tune?